All right. It's 2:40, almost 2:45, close enough, and time to go ahead and get started. I see there've been so I've already seen some good solutions to the Project 1 chips. I extended Project 2 was originally also due today, but I didn't get as far Thursday as I wanted on the arithmetic, and so I wanted to spend some time today going over that stuff. So Project 2 is due on Thursday. It's due on Thursday. I'm going to go back over 2's complement a little more today. I'm also going to discuss the ALU in a lot of detail today. So leaving aside those subjects, which are part of today's plan, are there any questions about anything, even issues that arose in the first project? Yes? Is Project 3 No, I have pushed everything back. So Project 3 will be due on Tuesday of next week, and then it supposed to be Project 3? It was originally due Thursday. Oh. And so Project 2 is now due Thursday, and 3, because I don't have enough, I'm going to probably start the memory stuff today, but I don't think, because I want to get the arithmetic right. I'm going to dedicate some time today and then all of Thursday to talking about the memory system to make sure those concepts are clear. And then I wound up kind of moving everything else back. I moved the midterm a little earlier, actually. It helped make the schedule work. So why don't I show you all that real quick. I have a revised schedule on the website. So yeah, so Project 1, that's the 30th today. Project 2 is now due on Thursday. Project 3 is then due next Tuesday, and then Project 4 will be the following Tuesday, 5 the Tuesday after that. Then on the Tuesday after that, we'll have our midterm exam. So the midterm will cover chapters 1 through 6. I was originally going to do 1 through 7, but I decided to just move it a little earlier. It made some other things work out better. So midterm will now be on the 27th, September 27th. And then, you know, I sort of adjusted the schedule out from there and nipped and tucked so that I could get us back on track after fall break, basically. So that is the both near-term and medium-term revisions to the schedule. So there it is. All right, other questions before we get started? All right, let's review 2's complement and the reason for it. So imagine that you have integers encoded using 4 bits. You want negative numbers. So if you have negative numbers, it needs to be the case that for any number x, if you then add its inverse, you get 0. And so what we saw last time is that you have to design your representation to bring this about. And if you're not careful, it's not going to work. And so what does work is what's called 2's complement. And to calculate the 2's complement of a binary number, the first step is flip all bits. And notice this is really just the same thing as doing a not to the bits. We're going to play with 4 bits for our examples, but in terms of the circuits you all have been developing, you know, not 16 comes in really handy here. Not 16. All of your efforts to produce a not 16 will pay off. And then second thing we need to do is add 1. And this basically makes it work. So this has a number of advantages. Among other things, we have only one representation for 0. It should always be the case that if you negate 0, you just get 0 back. And that really works well with this scheme, because if you've got 4 zeros you can perform a NOT on those 4 zeros, and you get 4 ones. Then when you add 1, you get all zeros again, with a little carry off to the side. But that's okay. If what we're concerned about doing is using addition to achieve subtraction, this can do it for us. So this 2's complement arrangement then is the most essential, most powerful tool for integer arithmetic using digital circuits. I am not presently aware of any CPU that uses anything other than 2's complement to represent its integers. I'm not going to say that there are none out there, because if I do, on Thursday, one of the very bright students in this class will mention it. I don't want to diminish the challenge of doing that. If you can locate such a processor, by all means, bring it up randomly on Thursday. I encourage that. But I certainly don't know of any, and it would be highly amusing to learn of one. So, but 2's complement works really, really well as a practical matter. Now, you can actually perform this conversion in some other ways, and this is going to be relevant when we look at the ALU. I alluded to this last time, but I kind of had to fly through it. Namely, the operation we do here, flip all bits and add 1, can be inverted. That is, we could also do this as subtract 1 and then flip all bits. And that also works. Why we would want to do that, I'll get into when we start talking about the ALU. But first, I want to show you that it does actually work. So first, let's examine our case of 0, right? So to subtract 1, of course, what does this mean? It means we're going to add a -1. So we're going to add all 1s. So this scheme, of course, assumes that -1 is all 1s. Okay, and that subtract 1 means add -1. So we do that, and of course we get all 1s, and then we perform our NOT, and now we happily have all 0s. So let's look at a different value. So let's try 2, for instance. So if we use this scheme with 2, we're going to first subtract 1. So we get 1. 1 plus 1 is 0. 1 plus 1 is 0. 1 plus 1 is 0. And then we got our little carry over there, which we will now forget about. So now we flip all the bits. We get 1, 1, 1, 0. So now, in contrast, right, if we had flipped the bits and then added 1, we start with 0, 0, 1, 0. We flip them, we get 1, 1, 0, 1. And now we add 1, so we get 1 plus 1 is 0. Bam, bam. Notice that we get the same thing either way. Now, intuitively, I hope you all can see that there's some nice symmetry between these, right? If the last thing you do is add 1, well, you can switch it around, make the first thing you do subtract 1, and then flip all the bits. It works out symmetrically. Works out symmetrically. So I had personally never thought of doing 2's complement this way until I had encountered the ALU in this chapter, actually. But I wanted you all to see the relationship between this sort of standard way of thinking about 2's complement and what you'll actually be building a circuit to do between now and Thursday. So any questions on that before we dive into the ALU? So let's review what the inputs are for the ALU. First of all, we have 2 16-bit inputs. These are designated X and Y. So all of the work you did in project 1 to create gates that manipulate 16-bit inputs will pay off handsomely here. For example, not only things like and 16, but most especially your new best friend, the multiplexer, is really going to pay off a lot. You no doubt went to some effort to construct the 4-way multiplexer 16 and the 8-way multiplexer 16. Hopefully you found those to be really, really easy once you got the trick, namely to build them out of the smaller multiplexers. So you get some really elegant solutions to those. In any event, you're going to be using these a lot to build the ALU. Why is that? It's because the ALU allows for a lot of different possible functions to be computed. So in effect, you're going to wire a circuit that always computes all of the possibilities and then uses multiplexers to pick which of those possibilities actually gets to exit the circuit. And that's really the key to making the whole ALU work. So let's talk about these bits that are going to control what it does. So there is ZX and ZY. What these do is replace X or Y with all zeros. I alluded to this last time, but it never hurts to repeat it. In Appendix A, which you'll definitely want to be familiarizing yourself with if you haven't already, there is mentioned how you can set something to a constant. In particular, on page 286. You'll want to read over that carefully. It talks about how to set either all or part of an array of bits to either be true or false, with true being ones and false being zeros. In office hours, I had a conversation with someone, don't remember who, but true and false are all lowercase. All lowercase. Capitalize the T in true, suddenly it's no longer true, it's something else. And neither us nor the simulator know what. So you'll want those to be all lowercase. So that's mentioned on page 286. Note that the way that this works, you're going to apply the zeroing before you apply any other functions of the ALU. So the next step is NX and NY. And these are to apply not to either X or Y. Okay? So if both the Z and the N for an input are activated, what does that input become? Sure. The Z is applied before the N. So if you have both the Z and the N, let's say for X, if you activated both ZX and NX, what is X now going to be? What, sorry? One. There's a big difference between 1 and 1s.
Like each one of them will be a 1.
Correct. Yeah. So why is there a big difference, right? Because 1 is going to be 15 zeros and a 1. 1s, that would be 16 ones. That is more what we're interested in. Now, the arithmetic value of that in practice is going to be what?
A big number. 9.
-1. Right? Remember, we have to think in 2's complement land, right? So if we have all 1s, it's actually going to be -1. Very interesting. So the effect of setting both of those to 1 is to fix the input at -1. Curiously, there's no way to fix the input at, say, 1. But you can fix it at -1. Okay. So there's 4 of the flags. There's still 2 more flags. So flag is 1 bit that signals a true false value. So yeah, I just realized I hadn't actually defined that term. So a flag is just a 1-bit value that either signals something is true or something is false. So all of these guys are flags, and we'll be looking at some others as well. Flags can either be input or output flags. These are input flags. There are going to be 2 more input flags. They're going to have 2 output flags as well. Okay. So the next input flag is called F. It is F as in function, namely, which function of x, y do we compute? Since it's a flag, there are only 2 choices. There are only 2 options. F is 1, it'll be x plus y. F equals 0, it'll be x and y. Okay. Then the final flag is NO. And this is, do we not the output? This is the last thing that happens. So your ALU is going to do all of its processing prior to deciding whether to apply a not to the output based on the NO flag. I'm emphasizing this because to get the ALU working, you really need to get the sequence of events correct. If that sequence is off, you're going to get interesting results, but not in a good way. I mean, I want your results to be interesting, but not that kind of interesting. So we also have 2 output flags. So we have, of course, out, and that's a 16-bit output. Okay? But we also have 2 output flags. So these are 1-bit outputs that say something about what got computed. Okay? So the first of these output flags is ZR. And basically what this is saying is, if we are sitting on 16 zeros, this is going to be a 1. Otherwise, it's going to be a 0. Okay. So you need to examine your output and see if it's got 16 zeros. Nothing but zeros. If it's nothing but zeros, it's good. If it's got any ones, not so much. Yes?
When you say the out 16, like, I'm confused. What is going to be 16 zeros? What is it?
Oh, the output itself of the ALU.
But isn't this the output? Like these are the flags?
Well, there's output and there's output, right? So there is, that's a great question. It's a great question, okay? There is the 16-bit arithmetic output, which is always going to be the result of one of these 2 calculations right here. So whichever of these guys we pick is going to be out.
Right.
The output flags are telling us something about out. So the 0 flag is telling us is out 0. And so if out is a 0, then we get a 1. Okay. Otherwise, we get a 0. And then there is NG, which is basically saying if out is negative, that'll be a 1. Otherwise, it's a 0. So you'll have to have some circuitry for these 2 output flags that actually uses the output itself as an input. Okay. So that's sort of the whole superstructure. I want to pause for questions here before I go into the chart on page 37 that talks about the actual functions that the ALU calculates based on these settings. Yes?
What's the point of NG?
So NG is telling us, is it a negative number?
Right. What difference does it make?
What difference does it make? So that's a great question. What we're going to be doing with this is once we create the CPU itself, some of the instructions are going to have their behavior change based on those flags. So this enables us to do what's called conditional execution. So we can have a machine language instruction that only executes if a particular flag is a 1. And so that turns out to be really handy. So you can have conditional instructions. It's not something that tends to have an exact equivalent in high-level languages. It's something we trust the compiler to generate for us as a matter of course. But you can write just absurdly efficient code by doing stuff like this, where you have like all the instructions for an if block that then have a little flag on them, and then the instructions for an else block you can sometimes do. Other times, if you're doing more arithmetic, of course, the flags are going to change. And so then these get used with jump instructions, to make sure that you jump to the right location in the code. And we'll be playing with all that in the next few weeks. So, so on one level, it's like I could say, for now, just trust me, dang, these are useful. But to get the full context in, it's a way of enabling the CPU to decide via a multiplexer, of course, whether or not to actually execute a given instruction. Good question. Other questions so far? All right. So let's see what these flags do as a practical matter. So on page 37, it actually lists off, okay, if I have this combination of flags, this is what my output is. So it starts with some that are kind of simple and innocuous. So if you've got something like, let's see, whoops, ZX, NX, ZY, NY, F, NO, and then we get our output. So we're going to go over some of these. Of course, these are all in your book, but I want to talk through why they work the way they work. My goal here being to help you understand what the ALU can do for you and why it works that way. And I think that'll help you to visualize how you're ultimately going to put the circuit together. So let's say turned on both your zeros, okay? And then you add them, and then you don't negate the output. So if you've got x of 0 and y of 0, and you add them, what do you get? 0, yeah. So you can use that set of flags to always give you a 0, which has its uses. Now, let's say you want a 1. Actually, let's do -1 first. It's different than the order in the book, but I think it'll illustrate something kind of interesting. So to get a -1, what we can do is set both ZX and NX to be 1. That makes X a -1. Now we set ZY to 1 and NY to 0. That makes Y a 0. Now if we make F1 to do addition and NO a 0, we don't want to negate it, we're going to get a -1 every time. So, so that's how we can get a -1. What if we want a 1? So 1 is a little more involved. What the book suggests is let's actually make X and Y both be -1. We're going to make both of them -1. Okay? And then we're going to add them. So if we add -1 and -1, what do we get?
I'm thinking.
-1 plus -1. -2, yeah. I didn't want you to think too hard. We want to save the harder thing for later. Yeah. So let's think about what -2 looks like as a binary number. If we imagine 4 bits, where, oops, 2 looks like this. We do our first complement, then we add our 1, and now we have 0, 1, 0, 0. No, sorry. That would be really sad if what I had written was actually it. Yeah, there we go. So that's our -2. So if this is -2, and now we apply a not, so we're going to negate the output. We flip all the bits, and hey, we have +1. So this is a pretty weird row, right? So this is actually the second row in the book, even though I did it as the third row up here. It's pretty weird, right? You set x and y to be -1. You add them, you get -2, but now by inverting all the bits, you get a nice +1. For the reasons I just showed you right here. So that's how that works. So let's walk through some more of these. So let's say we set both of these to 0 for a change. So we're going to let x go through unimpeded. Okay. Y, however, we are going to transform into a -1, 16 ones. But now we're going to do something different with f. We're going to make f 0, and we're not going to negate the output. What are we going to get? And basically what we're doing, right, is we've got x, f is 0, so we're doing an and. Then we're going to have 1s as far as the eye can see. What's that going to give us?
Bunch of zeros followed by an x.
Well, okay. Imagine we've got, like x sub 15, x sub 14. So we've got a bit for every, yeah, x sub 13, going on.
Yeah, root of x is 1, then you add that, so you get 1. But whenever x is 0, you get 0, so you get just whatever x is.
That's exactly right. By doing this, we actually just get, oh, this was +1, by the way. We actually just get x back, okay? And this is a really important use of and. Right? If you ever use and with all 1s, you preserve what came in. What would happen if you used or with all 1s? It's always all 1s. Yeah. What happens if you and with all 0s? You have nuked it. At that point, you have destroyed it. To get math geeky about this for just a moment, all 1s is the identity element for and. Okay, it's the identity element. In other words, it preserves whatever comes through. It's like multiplying by 1, and anding by 0 is an awful lot like multiplying by 0 now, isn't it? Yeah. So that's very important. That's the identity element for 1. So we can get a closely related function, which is just give me y by switching these around and leaving the rest alone. So here we turn x into a bunch of 1s. Y is just what it is. We and them. We don't negate the output. We get y. And so that preserves y going through the ALU. That'll preserve y going through the ALU. A lot of these operations are going to be very, very important when we are defining our CPU, because often you're going to have instructions that only affect part of what happens, and so it's really helpful to be able to preserve values going through ALU. All right, so with just a small change to these two rows, we can get two more values, right? So if I want not x and not y, I can just copy these, except I change NO to be a 1. Change NO to be a 1. And so the exclamation point is a common syntax used to denote not. It's certainly what the book was using there. So, again, that's a pretty straightforward extrapolation from what we've been doing. So we have gotten to the screen is full part of the chart. So I'm going to go ahead, create a new slide, and start drawing the second half on a fresh page. Okay. So let's just recreate our header. Oops. All right, so now things are going to get a little more involved. For this next row, we're going to leave x alone. We're going to turn y into all ones. And now we're actually going to add them and negate them. So let's walk through the kind of result we might expect from this. So I'm going to use just 4-bit values for illustration purposes. So let's say my x is 3 in 4 bits, 0, 0, 1, 1. So I am faced with a y that's all ones, and f is 1, so I'm going to add. 1 plus 1 is 0, 1 plus 1 plus 1 is 1, carry 1, 0. 1 plus 1 is 0. Bam, throw that away. And now notice that NO is out. So this was 3. Okay. This is -3. So this is the 2's complement operation in the ALU. This is what I was talking about at the start of class, where what we did was we subtracted 1. So this is -1. And then we flipped the bits. And so the reason our ALU is set up this way to perform a 2's complement is because it leverages the control bits that are already in place. Now, it would be a different sort of class, very interesting, but very different if we were concerned with actually designing an ALU from the ground up, like making up your own specification for an ALU. I mean, that would be really interesting. That would be a more advanced class than this. What we'd be getting into there is, how do we come up with a minimal set of flags that can hit all of our key operations? And so that's what the designers of this ALU were attempting to do here, was come up with a minimum set of flags that let you do everything with as simple a circuit as possible. Because by itself, this is arguably not terribly intuitive, right? But it's effective because it's leveraging the limited number of flags that are in place. So, of course, we can just switch these around, and we get -y. So we can 2's complement y in addition to doing a 2's complement of x. So next row gets us x plus 1. So how do they extract an x plus 1 from this thing? We're not going to 0 x. We want to keep x if we're going to do any math with it. But we are going to negate it. We're going to flip all of the digits. And then we're going to set y to be all ones. Then we are going to add them. and then we are going to negate them. And somehow this gives us x plus 1. So let's walk through an example and get a feel for how this might work. So let's go with 3 again. 0, 0, 1, 1. So this is going to get negated. So it becomes 1, 1, 0, 0. Okay? Then we're going to add to it 1, 1, 1, 1. In other words, we are subtracting negative 1 again. So that gets us 1, 1, 0, 1. And now we're going to apply NO to this. That gets us 0, 1, 0, 0, which is absolutely 4. So essentially what it's doing here is lots of layers of nested negations, the outcome of which is the positive value that was sought. So again, we can do the same thing for y. So if we set x to be a negative 1, we let y go through, set our function to add, and that to negate. Wow, that was the worst y like ever. Let's try that again. That y is not good, but it's better than the last y. So that gets us y plus 1, which is very nice. Okay. So after all of these more Byzantine transformations, I think we'll find x minus 1 to be a lot simpler, right? Because we can just leave x alone for a change. We can set y to be negative 1, set the function to add, and not negate the output. So we add a negative 1 to x. There we are. You know, we don't have to think too hard about that. I'll skip y minus 1 for the sake of space. Let's see. Well, just for completeness, let's go over x plus y. Leave x and y alone. Set f to 1. Bam! We get x plus y. Very nice. Very nice. X minus y. This one's a little more involved. So we are going to flip all the bits on x, and we're going to leave y alone. Then we're going to add them and negate the result. That'll get us x minus y. So let's do an example to try to think this through a bit. Let's let x equal 4. Let's let y equal 3 and explore how this calculation works. So if x is 4, not x, so 4 is just this. So not x is going to be that. Then we're going to add to that 3, which is this. Carry 1, 1, 1, 1. And then we not it, and that gets us 0, 0, 0, 1, which is equal to 4 minus 3. It's 1. And so that works out really nicely. Then y minus x is just symmetric to that. You can put, to get y minus x, have a 1 there and then zeros here. So x and y, well, this is a simple one, right? You leave x and y alone, you set the function to 0 for and you don't negate it. So in other words, if you stick all zeros all the way across, it'll do x and y. More interesting is x or y. So this vertical bar is often used to mean or, this vertical bar. So x or y, this one's going to be a little more involved. We're not going to zero either of our inputs, but we're actually going to not both of them. Then we're going to do an and we're going to not it again. So this is taking advantage of the following properties with Booleans. So, De Morgan's law. So what's the idea of De Morgan's law? Well, if you have not x and y, that's going to be equal to not x or not y. And so this is just a well-known algebraic lemma. We can prove it with truth tables if we want. Okay, and it also has an inverse, so not x or y is not x and not y. But this is the form that is being applied in the bottom row of this table for the ALU. Now, how is that? Well, we negate x and y, okay? So we start with x and y, and now we're going to negate them. So we've got not x and not y. And now we're going to ask the ALU to AND them. And once it's done that, we are going to negate the result. So to understand how this works, we look back at De Morgan's law, and this is an equivalence, so we can apply it in either direction. So what we have is not, oh, whoops. We're using this form. Sorry about the mix-up. Okay. So we can substitute this in here. And then our nots cancel each other out. And what we have left is x or y. So interestingly, we can coerce our ALU to perform an OR without it explicitly using an OR gate. Now on the surface, this might seem pretty silly because it's like, well, why not just stick a dumb OR gate in the thing, add a control bit, and make your life easier? And the answer is, this gets down to the design of the CPU. We want to minimize the total number of control bits. Ultimately, these control bits are going to be components of machine language instructions. So if we added more control bits, we would need fatter instructions. So by minimizing the number of control bits, we can minimize the width of an instruction. That, in turn, induces us to find ways of computing common functions without necessarily including them in an explicit manner. Every instinct in you that's saying, but this is not efficient, I can already feel it in the room. This is not efficient. Well, you're kind of right, and we're going to talk more about that when we talk about memory. The more levels of gates you have to get to an answer, the longer the electricity takes to travel and the slower the CPU is going to be. So that's just a bit of a design trade-off. It's not a sin, though. It's just a design trade-off. So that's the ALU, all told. It's really not that difficult a circuit to build. The key insight is to understand how these control flags affect the inputs. Your inputs will come in, and every control flag forces it to make a decision about which value gets to keep going further. And so using these control bits in conjunction with multiplexers, which by the time you're done with this should be like your new favorite circuit ever, should enable you to get a nice working ALU going for Thursday. Cool. Any questions on the ALU? All right. So just to review for Thursday, and the goal is you've started these already. won't always have been achieved, but for the most part, I'm hoping it has, right? You've got the half adder, the full adder. Okay, I'll mention here, just as you may have found with the big multiplexers, you can often build complex circuits out of simple ones. You know, here you can use 2 half adders plus 1 mystery gate to put that together. Just one mystery gate. Okay. Half adder is pretty easy. Then you're going to do add 16, which is going to be, you know, army of full adders. Kind of like and 16 and not 16. You'll have 1 half adder in there too. Okay. Increment 16, and here what I suggest is use that and add 1. Then finally you have the ALU itself. And so, of course, in the heart of the ALU, you will absolutely be using add 16, and you won't want to forget your friend and 16 from project 1. And then mux 16, all numbers of ways may come in handy there as well. And there'll be various auxiliary places where you use other gates in addition. So put it all together, you've got the arithmetic core of a computer. The ALU, in some ways, I think will be one of the more complicated parts of the CPU. But by itself, it's not really enough. You know, I've mentioned before how multiplexers are like the if of the circuit world. But there's a pretty big thing we're missing. You know, we can talk about the if, conditionals, we can talk about the math. But how on earth would you ever do something like a loop? Or for that matter, any sequence of computations? I mean, as it stands, these circuits, I mean, they're kind of cool, they're kind of fun, but they have this idea of simultaneity about them. You know, it's all stuff that's happening at once. I mean, it's not really at once, like we've talked about, speed of light kind of gets in there. But it's all stuff that's essentially concurrent. But as we know, that's not really how computers work, right? What really makes computers powerful is the idea that you can execute instructions in a sequence. By executing instructions in a sequence, we have powerful things like loops, which then can take us anywhere. The question is, how do you get a sequence? Now we're going to start moving into chapter 3 kind of material. I'll start that stuff today. What's essential to the idea of a sequence is fundamentally the idea of change. You know, you could imagine building some arithmetic circuit, and every time you apply some new input to it, it'll add things right or subtract things or whatever, what have you. But it doesn't have any memory, right? If we want to represent the idea of change, we have to have an idea of memory embedded in this thing. So the question is, how do we remember? How do we remember? How do we change state? This is a pretty complicated process, and we're going to go through it pretty slowly, actually. Okay. So I'm going to start by sketching out a specification for a circuit that changes. Okay. We're going to say that this circuit has 2 key inputs. set and reset. And then it'll have an output as well. We're going to say if set is 0 and reset is 1, we're going to define the output to be 0. In other words, we're saying we want to reset the value to be a 0. We're flushing the value. Set is 1 and reset is 0. We're going to say we want this to be a 1. We're creating an output. If we set to 0 and reset to 0, in other words, we are neither setting nor resetting. This is where memory comes in. What we want is our old output. Obviously, this is going to be weird. It's going to be a little odd. Bear with me. So let's set up our inputs. We have set and reset. And to build this circuit, we are going to use NOR gates. I'm going to use NOR gates. So there's one NOR gate. There's another NOR gate. And we're actually going to do something a little funny for the output. We're going to have two outputs. Now, I've been calling it out. The convention is to call it Q. So we would have Q here and not Q here. So these should always be the inverses of each other. Okay. So reset goes in here. Set goes in here. And now here is the crazy part. The outputs are actually going to feed back into the inputs. So Q is, whatever Q is going to feed back into whatever set's NOR gate, and then not Q is going to feed back into reset's gate. So this circuit, in terms of the layout, is fairly simple, but good God, it looks weird compared to what we've been doing. We're going to try to walk through this really slowly to get a feel for how the circuit works. So this is going to look like a truth table, but it's actually going to be kind of a weird truth table. It's more of like a sequential truth table. It's going to show how these values change over time. So we're going to have the set column, the reset column, the output, and the negated output. And so for each row, we're going to use the output and negated output to guide what we're doing. So let's assume that set and reset both start at 0. Let's remind ourselves what a NOR gate does. So a NOR gate is a 1 when both the inputs are zeros. Okay. And it is a 0 otherwise. Okay. So let's assume an initial value of 0 for Q and an initial value of 1 for not Q. So we get Q NOR set is our new not Q. So our old Q, 0, NOR set, gives us a not q of 1. Our old not q is 1. So 1 nor 0 is going to be 0. So notice what's happened here. Just to have a starting point, I designated q to be 0, not q to be 1. S and R are both zeros, which means we produce the old output. So far this works. So next, let's go ahead and change something. So we're going to set S to be 1. We're going to leave R at 0 and see how this calculation proceeds. So set, coming up to set, is a 1. Set gets NORed with Q, right? So Q is coming in as a 0. Wait a minute. To produce not Q, that's right. So Q is 0, S is 1, 0 nor 1 is 0, not Q changes to 0. Okay? What about reset? Reset is getting, let's see, not Q, right, not Q, which is now 0. 0 nor 0 gets us a 1. So now we've switched the states. Let's reset it. So we get S is now 0. Q is coming in as a 1. I've messed this up somewhere. Let's see. If we have 1 nor not Q. Oh yeah, we start with R. So we have reset. Reset is getting NORed with not Q. That produces the 0. The 0 is now getting NORed with set, and that gives us a 1. You can imagine that the current basically just keeps flowing through this thing until it reaches a stable state. If we now set it back to 0, the results get preserved. So 0 NORed with not Q gives us our Q. 0 NORed with Q, 0 nor 0 gets us a 1, and we're preserved. So this circuit is called the SR latch. It's called the SR latch. And this is the most basic sequential circuit with some memory. So now I want to invite you all to consider the following. If the SR latch is a component that you're given for updating memory in some form, how convenient is the interface? That is the idea of S and R for changing values. Thoughts? Like, what kind of interface might be easier to manipulate in terms of putting it in a circuit to store a value? Yeah.
Honestly, I have no idea what you're asking.
Okay. So let's say I want to store the result of 2 bits going through an AND gate. All right, so I've just got 2 values coming in. They go into an AND gate. I get some value, and I want to save this value. Now, as it stands, what I need to do is I need to make my S a 1 and my R a 0 in order to save that value. Now let's say a 0 came out. I would need to make my S a 0 and my R a 1 to save the value. This would work, but I'm suggesting this is a little clunky, you might say. And so I'm inviting suggestions about what might be a little less clunky than having to set these S's and R's. Thoughts? Yeah.
You can have them. So I'm just trying something.
That's the idea.
You can have the S and R to be fixed at 1 and 0, and have another latch that's the opposite.
Okay.
And this way, depending on the outcome, you can use like a multiplexer. If like the outcome is 1, it goes through this latch. If it's 0, it goes through the other latch.
So that's a really neat concept, in fact. So the idea being it's just sort of set in a particular way, and then you use a multiplexer to clean it up. That could be a neat implementation of a cleaner interface. I think what we're really getting at, and I think what we're suggesting with the multiplexer, is this would be cool as a select bit on a multiplexer or demultiplexer of some kind. So that we don't have to do this translation of taking one bit and turning it into 2 bits. Yeah. And that's really what I was getting at in terms of making a more convenient interface. SR is pretty clunky. It exists because it works, basically. What I'm suggesting is we can build a circuit on top of this that's a little easier on the designer of the circuit. So the design I'm going to outline for you now is called the D latch. And so the idea of the D latch is it's got 2 inputs, data and set. The idea being data is just the value we want to store. Set is controlling, do we change? Is now the moment we want to update the memory. And so this turns out to be a much more convenient abstraction for thinking about sequential memory. That's because we can tie the output of some circuit directly into the data input without having to mediate it in SR terms. Then we can use, once again, the output of some multiplexer to decide whether we're changing now. And so this turns out to be a much more convenient design. The thing is, SR is what we start with, and so we have to get there somehow. We have to get to the SR latch using our D latch. So here's a way we can do it. So we're doing on time. We're doing all right. So set in data. We'll have set be the input to a demultiplexer. And we'll have data actually be the control bit for the multiplexer. And demultiplexer, as I'm sure you all know, are all now painfully aware, has 2 outputs. Right? 2 outputs. 2 outputs. Curiously, the SR latch has 2 inputs. So what we can do is put down our SR latch, and then here it's 2 outputs. And we can use the data bit that's coming in on the D latch to make decisions about S and R. So help me wire this. help me wire this. So the possibilities, right? We've got data and S. So data could be 1s or it could be 0. Set can be 1 or 0. And what we want to produce is the correct SR combination. So why don't we think through these combinations? So if my data is a 1 and my set is a 1, what do I want for my SR latch? So it's just so the S and the R.
We didn't talk about when they're both 1 with the SR.
There's an excellent reason for that, which we might not quite have time to talk about today, but can absolutely be the first thing we talk about Thursday. So for now, we'll say you don't want S and R to both be 1. We'll just say that's bad. And we'll talk about why it's bad on Thursday. So if the data is a 1 and the S is 1, what do we want S and R to be? First of all, do we want it to change? Yes. Yes. We do want it to change because we're telling it we want you to set your memory to whatever your data is. So we do want it to change. Actually, maybe this will help. If S is 0, what are S and R? If S is 0, what are S and R going to be? They're both going to be zeros, yeah. Because if S is 0, we don't want change. We don't want change. So if D is 1 and S is 1, what should S and R be? We know it's not both zeros because we want change. We know it's not both 1s because, well, I told you. But we'll talk about that on Thursday. Yes? Good. We want S to be 1 and R to be 0 because that way it must become a 1. Our data is a 1. That's what we want it to change to. So fill in this third row. What would S and R be if D is 0 and S is 1? It's going to be 0, 1, yeah. So let's come back to our circuit over here. How do we wire this demultiplexer to correspond to the truth table on the right? So we can refresh our memories a little bit, right? So demultiplexer truth table, we have in, select, A and B. All right. So if the input is 1, select is 0. Anybody remember what A is? 1. And B? If my input is 1 and my select is 1, what's A? And my B?
1.
If my input is 0, well, it doesn't really matter what my select is, does it? It's going to be zeros all the way across. Hey, check it out, folks. Is there a pattern here, maybe? So how do we wire it? Yeah.
I think the top output from the demux goes in QR.
Okay.
And the other one goes across.
Goes here?
No, all the way around.
Huh?
Like I was thinking we can make it like we did up.
Oh no! Oh, all of that recurrent stuff is subsumed inside the box.
Oh, okay. then you have one. That's my second best guess.
Or it was me interpolating the correct answer into your guess. So let's, in all seriousness, though, let's look at the pattern, right? We're using set as our input. This is very, very important because if we don't want change, we want 2 zeros coming into the SR latch. So by making set the input, if that's a 0, it's going to route zeros to both of those guys. Okay, and so that takes care of this case and this case. Now, if my data is 1, that is going to activate the B output of my demultiplexer. The convention for drawing the SR latch is to have the S on top, so I have to cross the wires to get the S to the right place. The other one has to be a 0, right? Likewise, and so that takes care of this case. Now, if my data is 0, I want my reset to be a 1. And so to do that, I make my, I wire up my A, come down to the reset. And that gets me my D latch. This D latch is a really, really powerful idea. We now have a circuit to which we can wire the output of some other circuit and something that helps us make a decision. Something that helps us make a decision. And then decide whether to store that value in memory. And that memory, in turn, is built on this recurrence with the SR latch. And so this gives us the building blocks of memory. Okay, well, we do have a couple minutes left. So instead of moving on to the next memory circuit, we're going to come back actually to this issue of S and R both being 1. So I promised to talk about first thing on Thursday. We got enough time to talk about it today. Let's say set is 1 and reset is 1. My question for you all is, what does that mean? Yes?
You're constantly setting and resetting the same value.
I guess that's a possible meaning. Set is 1 and reset is 1. Then we want the output to be both 0 and 1 at the same time, right? Because an S of 1 is saying we want the out to be a 1. An R of 1 is saying we want it to be a 0. So if we make both of these 1s, we want the output to be both things at the same time. How useful is that idea? How useful is that? It's going to drive you crazy, right? And not only is it going to drive you crazy, this circuit will then become unstable. Well, hopefully it won't melt, but it's not going to stabilize on a value. It's not going to stabilize on a value. And since it doesn't stabilize, it's kind of useless. But the really important lesson when you take away from this is not only does it not stabilize, this really just has no meaning. You know, it's a contradiction. And that contradiction is essential for this circuit to work. In other words, we say this is outside the territory of what we're going to allow, and that lets us get away with this design. And that's a first for us. We haven't done that before. All of our circuits have had total definitions up to here. Fortunately, you're not going to be using SR latches all that much. You're certainly not going to have to build one. So it'll always be nice and safely encapsulated within a data latch or data flip-flop, which is what we'll talk about on Thursday. All right, very cool. Good luck on your ALUs. I'll just warn you ahead of time, if you want to find me tomorrow, get me in the morning. I have lab all afternoon tomorrow afternoon. I might be able to catch a couple people in the 4 to 5 time frame, but for the most part, I'm going to be really only around in the morning. So I just wanted to give you a heads up about that. All right, see you Thursday.